Warning: the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is a final video on areas and distances for a differential calculus class, or could be the case that maybe you're taking calculus at a different college, and sometimes this topic is covered in a Calc 2 class. Doesn't matter which, it's still the same topic. So we're going to round out this this whole video series on areas and distances by talking about distances. We've really focused only on areas so far. And the concept of using Riemann sums for distances is really an application topic. So that's why I'm just doing a couple applications in this video. So let's take a look at this first example. Speedometer readings for a vehicle at 15-second intervals are given in this table right here. Estimate the distance traveled by using the midpoint method. Now this was kind of the opener in a way to this whole entire video series. So I gave you a graph, and it didn't really matter what the graph looked like. What mattered was that the units for the vertical axis I think at that time were meters per second. We're going to call them feet per second to match this data. And then the horizontal units, or the independent variable, was in seconds. Well, if you think about an area underneath this curve from time A to time B, we had talked about this again in the very first video in this series, but this area is in essence a width times a height, and if you take the width and multiply it by the height as far as units go, you would get feet per second, that's the units for the height, times seconds, that's the unit for the width, and you can see the seconds units cancel beautifully, and you'll get a certain number of feet. So this is actually, whoops, I was writing f of x. This is how you can interpret the area. It's just the product of the vertical unit and the horizontal unit. At least that gives you an idea of what the area represents. So in this case right here, the area underneath that curve where the y values are represented by these velocities is going to be the total distance traveled in that time, or an approximation for it. Now, I'm not going to bother graphing out these data points because one, it takes a while, and two, there's no point to do that. Really what they're asking us to use is the midpoint method, and I really want to showcase that idea with a table, because of all of the methods, the midpoint method is the one you have to be the most careful of when you're working with a table of data. So recall that the midpoint method is the following. It is the summation of the heights times the widths. So basically summing up a bunch of small areas. In this case, the heights are going to be found at the average of the edge points. So you recall when we derived the method, and by the way, it's assumed that you've seen all the videos up to this point, so I'm not going to really derive the entire method. But when we derived the method, we had a full interval from A to B, and then within that full interval from A to B, you had a bunch of sub-intervals, and the ith sub-interval was this one right here, x sub I minus 1 to x sub I. If you were using the left endpoint method, then you would evaluate the function at the left edge. And that's why the argument for our function would have been, if we were using the left endpoint method, just f of x sub I minus 1, or x sub I minus 1 would have been the argument. However, if you use the right endpoint method, let me go back over there. If you were to use the right endpoint method, well then you would use x sub I. And that's why the very common method for the Riemann sum for finding the area underneath the curve, is to evaluate your function at the right endpoint, x sub I. With the midpoint method, you're averaging out those two. You're finding the middle point. So the midpoint method just uses the average point. And this is the oddity when you're working with a table of data. Table of data here, you can't create a point between 0 seconds and 15 seconds. You just don't have enough data to do that. So unfortunately, we cannot say, oh, at 7.5 seconds, this was the velocity. We can't create that. So when you're using the midpoint method with data, your given set of finely tuned data here has to be split in half. So think about it this way. This time value really would be t sub 0, but I'll do that. It's t sub 0 or t naught. And this would be our first time value, or t sub 1, and then t sub 2, and t sub 3, and so on and so forth down the line. And what we want to do is use midpoints, and we cannot create any. So if you think about the interval, if you're going to create a midpoint or get a midpoint, you're going to have to use 15 as the midpoint between time 0 and time 2, because that's the only middle point you have from the get-go, right? So you can't say that t naught is a middle point because it's not in between 2 points. But you can say t1 is a middle point because it's in between 2 given points. Now you don't want to say, well, t sub 2 is a middle point, because really when you take midpoints, you're linking up intervals like this. So let me just showcase a few ones. You start at t naught, and in between t naught and t2 is t1. In between t2 and t4 is t3. In between t4 and t6 is t5. And so your midpoints would be t1, t3, and t5. It really is a very coarse method to use. However, I've highlighted in the table the points we're using. Rather than using like 6 of those points, we're only going to get to use 3. It turns out that the midpoint method, at least for tables, is not the best, but it's great for many other methods. But for tables, it's very coarse. Let's go ahead and use it here. So we are going to use the midpoint method with 3 sub intervals, mainly because, again, we just don't have enough data there. And this will be equal to, we have to find out what delta x is. So delta x is equal to, actually it's delta t, sorry about that. I will commonly do that, mix up variables like that. Delta t here, you would think that it would be 15-second intervals, right? Because that's what they've given us. Unfortunately, if you look at the midpoint method that we are using, we're using 30-second intervals between edges of our intervals there. So between t naught, which is time 0, and t2, which is time 30 seconds, that's a 30-second interval. So that is actually our delta t is 30. It's very frustrating to use, I think, midpoint method on tables, but it's often a method that you're forced to use. So let's go ahead and do this now that we have delta t. We're going to take our function, which is just a velocity function. So I'm going to say velocity at time 1 times delta t plus velocity at time 3 times delta t, and finally plus velocity at time 5 times delta t. And then we're going to insert those values. So that'd be the velocity at time 15 seconds times delta t, which is 30. I'm taking my time with this just to show you so that I don't lose anybody in this derivation. That's all. So you could easily have skipped all these little sub steps here. There's nothing wrong with that. I just like to make sure that everybody is sort of on board with the argument here. And finally, we sub in the function values 23, 24, and 27. So 23 times 30 plus 24 times 30 plus 27, again, times 30. And this is 2,220 feet. Remember, it's going to be a distance in the end. It is not, like I said, a ton of fun to do something like that, just because I like the left endpoint method or the right endpoint method for a table. But again, in a textbook, they'll often ask you to use a midpoint method. So this was why I chose to use the midpoint method on this example. By the way, if you are very interested in actually seeing that data, you could totally do that by going to Desmos, clicking the plus, and putting in a table there, and then you could just type in all the values. It's not as if it really helps you with this problem, but some people really like a good visual, and so that'd be nice to see. So I'm going to zoom out here so you can see that. There's the visual of the velocity versus time. Again, it doesn't help you very much with actually finding the area underneath this data, basically the distance traveled, but at least you can see here the data that you're working with. Last but not least, we're going to go ahead and deal with this function. You're driving to the beach and map out your rate as the function r of t is equal to 8t sine of 10t plus 23t. Remember that in calculus, that argument will be in radians. So please make sure that you understand that. Anyhow, where t is in hours and r is in miles per hour. So obviously the area underneath this curve, if I were to just scratch out a graph of it, which that is not actually the graph, but let's just pretend. Remember, the rate units are in miles per hour, and the horizontal units are in hours. Multiply miles per hour times hours, and you'll get miles driven. That's this piece right here, the shaded area. So let's graph this function using technology. We already know the meaning of the area underneath the curve, and then use L sub 6 to approximate the distance traveled in the first 3 hours. And actually, I'm going to wait until I'm done finding out the approximation to graph. So I'll graph at the very end rather than at the very beginning. Sometimes this just works better to do things backwards. Also, I think that it's very helpful to note that you don't really need to graph to do these problems. Although it can be very helpful, it's not going to be super helpful here. One thing to note, again, take your sample interval here, which goes from x sub I minus 1 to x sub I. Remember, that's your ith interval. And note we're using left endpoints, so our sample point in our Riemann sum is going to be x sub I minus 1. And that will dictate how you write the summation. So that'll be the summation I equals 1 to 6 of f at x sub I minus 1 delta x. And again, as I said earlier, I will mix up those variables very often. Those should have been t's. There we go. This is functions of time. All right, let's go ahead and then write in the information we need to complete this summation. So we'll need to know what delta t is. Well, they said first 3 hours, right? So find the distance traveled in the first 3 hours. So from time 0 to time 3. So delta t will be 3 minus 0, basically when we end minus when we start. And we're going to divide that by the number of slices, which is 6. And so that'll be a half. That's our delta t. And then we need a formula for t sub I so that we can plug in t sub I minus 1. Now, technically, I would tell you that t sub I is equal to a plus I times delta t, because that is technically the formula. However, we're dealing with t sub I minus 1. So let's go ahead and change that t sub I to a t sub I minus 1. And then instead of an I here, it'd be an I minus 1. That's the only difference. Now plugging in everything we need, remember, the interval goes from A to B, and A is 0, B is 3 in this case. So A being 0 plus the quantity I minus 1 times delta t, which is 1/2. And so we get the following for t sub I minus 1. It is just 1/2 I minus 1. We'll keep it like that. Okay. So really we're looking at this summation. The summation I equals 1 to 6 of f evaluated at 1/2 times I minus 1 times 1/2. Remember that 1/2 can be factored out of this summation because it doesn't rely upon the index I. So I'll write that out front. And then I'll go ahead and start with I equals 1. Plugging that into this, I get f at 0. And oh, by the way, I know the function's not called f, but I've written f so many times that I'm just going to go ahead and say that this function's name is now f. Sorry about that. Plus index up to I equals 2. Well, if I is equal to 2 here, you'll have 2 minus 1 times 1/2, or f of 1/2. And now you know you're just stepping by size 1/2. So f of 1, f of 1.5 or 3/2, and so on and so forth down the line. And we'll stop at 6, which would be 5 times 1/2 or 5/2. So I'll just keep going till I get to 5/2. There we go. And now I just grab a calculator because that's what I need to do to finish this out. I'm not going to come back to this page, so I just want to make sure that you understand that at this point, all we're going to do is grab a calculator and plug those values into this function, sum them up, and multiply by 1/2. Also, I'm going to graph this function so you can see it. But our result will be the number of miles that we have traveled in that total trip. So I'm going to show you two ways to do this. One, which is probably how you're going to do it if you have a calculator on hand. You just grab your calculator here. And if you cannot save a function into your calculator, which likely is the case, then you're going to have to essentially go through and type out all these values. So remember the function, I'm just going to write it this way first so you can see the function on your screen. The function was f of t is equal to 8t times the sine of 10t and then plus 23t. That was the original function. Now, if you have a calculator and you're doing this by hand, you're going to basically plug 0 into this, and you know that's going to be 0, so I'm not going to really worry about that. And then you're going to say, okay, now I have to plug in 1/2, and you're going to compute that out. So you're going to say like, oh, 8 times 1/2, which is a 4, times sine of 1/2 of 10, which is 5, plus 23 times 1/2, right? And so you'll get, that's the function value at time 1/2. You'll save that or write that down, and you have to go through each of those time values: 1/2, 1, 3/2, 2, and 5/2. That's kind of a pain. So I recommend, especially if you're doing online homework, I recommend going ahead and doing this a better way. At least if you're going to use the scientific calculator on Desmos, just say, okay, well, it's going to be f at 0 plus f at 1/2 plus f at 1. See, it automatically does it for us here. Plus f at 1.5 and plus f of 2 and plus f at 2.5. And remember, in the end, those are just the sums of the heights. We still have a width to multiply by, and the width of our interval was 1/2, so times 0.5. So we get 95.6 roughly, and what was that, miles? So 95.6 miles. That's one way you could do it. The long-winded way would be to sit there and type it out on a calculator, honestly. I would use either Desmos or Excel to do something like this, or Google Sheets. But another way you could do this is the way I taught you in the previous video, which is by using Desmos' graphing feature. And in this case, again, I'll just say f of t is equal to 8t sine of 10t. Oh, that's really pretty there. Let's see, plus 23t. I must be super zoomed out or something like that. A very good looking graph, right? And then what we're going to do is go ahead and just type in the words sum. And we're going to sum from time 1 to time 6 of f evaluated at. And then you have to have the values here. So that's the only part that we didn't do. Oh yeah, we did do. Actually, it was 1/2 times the quantity n minus 1. It was I minus 1 in ours. And then at the end, we multiply by 1/2. And you'll see, oh, this one is slightly different. What did I do differently? I'll tell you what I did different. I told you calculus only works in radians, and look, I didn't have it set to radians. Ha 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 ha. So be very careful, again, when using Desmos, because its scientific calculator will be auto set for degree. And so be very careful about that. So it should have been 92.04 miles. But its graphing calculator is automatically set to radians. Very, very interesting. Notice that double check really helped us out there, because I would have not noticed that. So interesting. Another thing I want to showcase here is the little coding that I did earlier. I'm going to turn off the grid here so we don't have to deal with that. And this was the link that I provided in a previous video. We're going from time 0 and we're going to go all the way up to time 3. So let me do that. And we're doing 6 slices and we're doing left edge points. So let me zoom out and see what this looks like. That's this function in black here is our rate function. And this is really just a terrible window. So I'm going to adjust my window to go from 0 to 6 in the x values. There we go. And a lot easier. Actually, I don't have to go to 6. I can go 0 to 3. That's fine. 3.5. There we go. There you go. So that is our rate function, something I did not want to graph by hand. And the fact that we're using 6 sub intervals. You can kind of see that that's a pretty terrible approximation, honestly. You can fix that if you, well, right endpoints don't look like they're going to fix that, but midpoints actually will do a pretty good job of removing that amount of error. Midpoints is usually a lot better. Another way you could do it is, instead of doing 6 slices, do 12. Right? That's a little finer detail. Or you can go up to 20 slices if you want, or you go even further. Right? So anyhow, that's it for this video. We are done with talking about areas and distances.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.